Yellow.
Okay. So how do you get hold of the coordinates in this case? Well, you cannot see yellow, so I hope you'll be able to see this one. Okay. So, you first draw a line parallel to this, and a line which is parallel to the other one. So this length is your 1, 2. So this length is your 2y minus x, whereas this length, this is your 2x minus y. Okay? So we used to refer to this kind of coordinate frames as oblique frames.
Excuse me, sir.
Yes.
Just in this example, so I mean, you gave us R2, and then you gave us a list that 1, 0, 0, 1. What is the other one? A? Is it another list as well?
Yes, I'm saying there are two bases. In fact, there are several bases. I have only given 2.
Okay. So are you attempting to show if these are the bases for R2?
Yes. Then you have your notion of coordinates completely change. And I'm trying to give the geometrical picture of this coordinatization. So, the original one for B is your usual one, which you know from almost all textbooks do this. But thankfully to the present ones, the older ones did a thankless job of doing with oblique coordinates, which people don't do it now. But that is exactly the basis here. A. When you have these two blue lines as your coordinate axis, you can still find what are the coordinates. Okay? And the coordinates become, as I have indicated, right? This part of the story is given by this number, and this part of the story is given by this number. Okay? So, who say that the coordinate frames will have to be orthogonal, which people usually nowadays think. But no, coordinate frames can be anything. Any pair of linearly independent vectors give us a coordinate frame. And this is the idea behind coordinatization. And this is the starting point of coordinate geometry. Okay? Alright? So, it is not the coordinates which is important. Which is much more important is the intrinsic geometrical picture. Coordinates can change, but the geometry is the study of not all of the coordinates, but the intrinsic properties. We will see how this geometry comes up. So here is the starting point that I am saying that you see now that you have the same point x can have the same point xy with respect to different coordinate frames can have different coordinates. Okay, so there is not the notion of coordinate is very much respect to a basis. Is up to a basis. You have a basis, you have a coordinates for that basis. You change the basis, the coordinates will change. Okay? There can be several points where the coordinates will not change, but the coordinates will change for some points. Okay? For instance, 0, 0. This one, coordinates over in B and coordinates in A are same. So not all points have different coordinates, but that is not the picture. I'm saying at least there is a point which has different coordinates. So the coordinatization is different. So now the next question comes, what the hell is this coordinates? If it is so much dependent on basis, then what is it? Well, that's what I'm going to tackle now. So suppose you have a vector space V with dimension n, and this is a basis. Okay? So we have just now seen that I can define for each member x over here, a member of Rn, which is its coordinates, with respect to the basis B. Okay? So it gives us a function. Good? So it's a function, firstly. Next, let us observe. You give me give me then, if I look into this, why? Let me, because it might be, let me take beta 1, beta 2, beta n. And let me put this to be some t. Okay? Then why? This is a member of V, coordinates of Y with respect to the basis beta, B is actually, and Y is the unique such. Why unique such? If you told me that the coordinates of a vector z was beta 1, beta 2, beta n, what is the meaning of it? It means that z is equal to beta 1 v1 plus beta 2 v2, etc. plus beta n vn, which is exactly y. So what did I see now? I see if I take any point from the codomain, which is Rn, there exists one and only one member in the domain which is mapped to that point. Okay? So this one is a bijection. So coordinatization, coordinates is a bijection. Good. Remember what I said in one of my first classes. What is a bijection? Well, it is just a kind of a dictionary. It gives a new meaning, new form. Okay? So however this vector space V might look like, this finite dimensional vector space, coordinatization is a way to recapture a familiar form to it, a familiar shape to it, namely via Rn. Yeah? But is this just a function? No. Let's see. Suppose x is, so I'm just writing. And y so then you know x plus some mu times y is alpha 1 plus mu times beta 1 b1 and so on. So what comes up? So what is the coordinates of x plus mu times y? This is alpha 1 plus mu times beta 1. Which is nothing else but alpha 1 plus mu times, which is nothing else but coordinates of x plus mu times the coordinates of y. So it is a linear map. So it's a linear transformation. So it's a bijective linear transformation. So I can say this coordinatization is a bijective linear transformation. So not only is it giving another shape to this strange V, but it is preserving the vector space structure. Okay? So whatever we might do in V, we might as well think of doing it in Rn. So what's the upshot of taking this V route? Well, there is only one thing. With V, we can simply forget about the complications of Rn. Okay, we don't have to think that it looks like an n-tuple and so on. Thinking becomes much more simpler, whereas Rn, it becomes a little more complicated. But the geometric flavor comes completely from Rn. And we are going to see how. So let us record this result. So we see that, I think this is T3, right? If dimension of V, the n with then is a bijective. In other words, every finite dimensional vector space, how does it look like? It looks like some Rn. Okay? What is this n? N is the dimension. Okay? So that's the upshot of this. So, for example, when we took this vector space, remember, your addition was multiplication and scalar multiplication was defined by x to the power lambda, right? These are the definitions. Okay? Alright? Now, observe. This is a bijection. And e to the power x plus mu times y, this is e to the power x times e to the power y to the power mu, so which tells me this is a bijective linear transformation. Okay? So however, this vector space might look like, so dimension, this is 1, and this map, this one sets up, shows that how R and positive reals, that's strange one. Yes.
Excuse me, sir. Sorry, just take it back. When you're giving us the EX plus mu y is equal to, so I understand that in terms of the exponential laws, but my question is, how is that preserving the addition?
Wait, what is this? This is actually e to the power x plus right? But this again is same thing as e to the power x times the scalar multiple of this. So what's the definition of plus in positive reals? It is actually product.
Yeah.
And what's the definition of scalar multiplication? It's taking powers.
Yeah.
That's
okay.
right.
Yeah, I see. How did you? Why is it EX plus EY? Am I missing something?
Why is? What is
you
it?
have EX. You have EX plus EY. You're saying it's the same as EX multiplied by E exponent Y.
And what is this? If you call this map to be f, this is f of x plus mu y. And what do you show over here turns out to be fx plus mu times fy.
Okay.
Right?
Okay.
So f is a linear map. It's a bijection and it's a linear map. Clear? So therefore it says that the dimension of this strange vector space is 1. So it's nothing else but in its form, however it might look like, it is as a vector space, it is nothing other than the reals. Okay? So that's the whole story. Clear? Okay. Now the next part. So you see, we are, so how does this relate with linear transformations? That's where I'm coming now. Okay? So.
Sorry, sir.
Yes. Yes.
Sorry to take you back. What you just explained now, I did not get it. What that gentleman was asking, like the e to the power x times e to the power y, and then multiply by that.
To the power mu, not multiply.
How?
E to the power y to the power mu.
To the power mu, yes, that's correct. Then how is it related to that plus, to the one that has plus there?
What is your addition? What is your addition in R positive in this vector space?
Yes,
what do you mean by this?
Yes, my question is, how is that one, the multiplication, related to the one that has addition below there? And the second part, what is the meaning of that?
Wait. One by one. The addition in this vector space is defined by this. Right?
Yes.
Clear? So, what does this line mean? This is something you're writing in positive reals. So this multiplication therefore means it is the addition in this vector space.
Oh.
Don't confuse this addition with this addition.
Okay.
You get me now?
Yeah, I think so.
Yes. Now the second step. This one. So what is the definition of scalar multiplication in positive reals? By scalar multiplication means you raise it to the power of that scalar. So this thing is therefore nothing else but the scalar multiplication here. Step by step, slowly. So in our positive, this statement actually means this line, right? And what does this statement mean? This is nothing else but fx plus mu times f1. So that shows that this function is a linear transformation. Slowly. The problem in most cases is not that it is not intelligible, but we do not see where the problem is lying. You were trying to say that this addition is same as this addition. No. The same symbol is used, but this means the addition that's why I wrote, in this vector space. And this means the scalar multiplication in this vector space.
Right.
Okay? Yeah.
Yes, sir. Thank you.
Okay. Good. It's always right to ask questions. There is no wrong or silly questions. Such things don't exist by definition. But what I want to point out, always, you must recognize this, that the trouble or the problem rests within us. We cannot see the problem, and that's why we say it's impossible or it's hard. The moment we can see the problem, the solution is automatically there, and the mist has cleared. Right? So the problem is within us. So how do I transform myself from this phase of not being able to see the problem to the phase of, oh, I can see the problem? So this transformation is done via maturity, via exposure. As you get exposed, you can then see the problem. Okay? So that's why I say you learn swimming by swimming. Okay? So, yeah, let's continue. No lectures. Okay, so you see, this tells us, therefore, something very fascinating, that every finite dimensional vector space of dimension n essentially looks like Rn. Okay, good. So how does it behave with linear transformations now? So we have a vector space V, and dimension of it is n, and say this is a basis, and we have another vector space, say W, its dimension is m, and let this be the basis. We have a linear transformation. Okay? Clear? Now let's see. I'll write like this to mean that it is an isomorphism. So with respect to the coordinates, with respect to B, I have this linear transformation here. I have also this linear transformation here. to define a linear transformation. I'm going to define one. How do I do that? Let's see. I'm going to define something here. Okay? So, to do that, let me first put down this matrix. Now, members of Rn. So if I have a member from Rn, I will alternatively also, instead of writing like this, when I like to consider this X as a vector, I'll consider this as a column vector. That means as an n cross 1 matrix. Okay? So that's my understanding. So let me make this matrix A, which is, what is the first column? It is the coordinates okay? So, how did I do? This is my first column. This is my nth column. So what is my first column? Is the coordinates of FV1. Remember, what is V1? V1 is the first member of the basis of the domain. So FV1, its coordinates with respect to the chosen basis A of the codomain. Second column is the coordinates of FV2 with that basis A, okay, and so on. So this is, remember, these coordinates are with respect to A, so they are actually each m cross 1 vectors. So this matrix is an m cross n matrix, right? Okay. Now, I am defining this linear transformation F star. What is it doing? F star of X is nothing else but Ax. Okay? F star of X is nothing else but Ax. I leave it to you to now to do this, because the rest is very plain and simple. So check. F star. So what am I doing is, so I have defined this map, right? So this map I compose. So F star composed with coordinate of B is equal to coordinates of A composed F. What does it mean? If you take any X in V, okay? The star of coordinates of Fx, what is the coordinates of Fx? Is the star of the coordinates of this, okay? So you multiply this matrix. So this matrix is often called, and this turns out to be the unique matrix. unique such linear transformation. So if star is a linear transformation which therefore determines or represents this linear transformation F. And this is called the matrix of this F. This is called the matrix presentation. With respect to the basis B and D. Okay? And I prefer this symbol. I write it in this way. So it says it is the matrix of F with respect to the basis B on the domain to the basis A on the codomain. Okay? Alright? And, well, this is. Is it getting heavy? There are a little more things that I should say about this. Should I continue or do I do it next time? Then it gets translated, but yeah. Is it getting heavy? Are the centers? Or do I continue?
You can continue.
Good. Okay.
No, you can continue with her. With her. Because you're taking for my that you're kidding me.
Next time, sir.
Too much.
Next time, sir.
Next time.
Okay, but we will have. No, don't run away because we'll be having our tutorial session.
No, next time.
So, you say that the theory would be much more difficult. Okay, I'll stop with the theory. But let's see. We will explain this with respect how. I'll quickly say something. Now, this therefore tells us completely what are the linear transformations from Rn to Rm. Why? From Rn to Rn, this one. Usually, we will always have, let me write it in this way, this bold U. This is, how do I write it here? Let me write it like a bold U with an N like this, okay? And this is this one. And what is this? This is this n tuple which has I 1 in the ith place. Okay? So this is an usual basis, and we shall usually write this like this, U with a N. Okay? Now suppose you give me an M cross N matrix. Okay? It's an M cross N matrix. So let's work out a special case. Suppose you give me a, say, so it is a 3 cross 2 matrix. Okay? Well, I'm saying that I will give for this matrix a linear transformation, which I'm still writing now as bold A. What is it? This linear transformation is from R2 to R3. And what does it do? Okay? Remember, I am saying that A is the matrix of this linear transformation with respect to the standard. So I want to make this as, so from U2 to U3. So what is this I know? I know this should be, so the first column should be where I will take this, where will be? So I know, so therefore, A of 0, 1, A of 1, 0. As the first vector in this U2, that should be 2 minus 3, 4. Oh, so 2, 3 minus 4. And A of 0, 1 should be 4, 5, 3. Okay? Telling this is enough. Why? Because therefore, what is A of xy? It is going to be x times A of 0, 1. So 2x plus 3y, sorry, where is it? 2x, 3x minus 4x plus y times this, so 4y, 5y, 3y, which is 2x plus 4y, 3x plus 5y, minus 4x plus 3y, which you see is nothing else but A times this matrix xy. Yeah? Yeah, so you see how quickly, given the matrix, you can construct the linear transformation. Okay?
Sorry, sir. Excuse me, sir.
Yeah.
Is there any particular reason why are you choosing? So why are you using like A 1, 0?
This is the matrix from U2. So I said UN is the standard basis for Rn, which looks like this. So I have taken the standard basis on R2 and R3.
Okay.
So with respect to the standard basis, the matrix, of this linear transformation. Yeah. Okay? So you see, given a matrix, so you now know the general fact that every m cross n matrix corresponds to a linear transformation from Rn to Rm. Okay? And these are all the linear transformations from Rn to Rm. Okay? So, you see how beautiful this matching, this thing comes up now. So every matrix is nothing else but a linear transformation. Alright?
Excuse me, sir.
Okay. Okay, I'll give you some time now. We will meet again after 10 minutes.
Excuse me, sir.
Yes.
The matrix now, when you say ax comma y, the coordinates there, so then you go 2x, 3x minus 4x. Can you just please explain that step?
Which one? So this bold AXY, what will it be? And you told me this bold A is linear. So it should be x times bold A of 1, 0 plus y times bold A of 0, 1. That's what I wrote.
Okay.
Okay?
Okay.
Okay? Yes. So that's the whole story, therefore. Get it? And what is this? How do you get this? This is nothing else but if you multiply A by this, I have written this now as a column vector, as I said. Points of Rn, if I want to look upon it as a matrix, I shall look upon it as a column vector. So if we multiply this, use the multiplication rule of matrices, you exactly get this. Right?
Yes.
So that's it. So that's it. Okay? So under this, we see that how beautiful it turns out that every matrices now become precisely linear transformations. Okay? Alright. I'll stop for 10 minutes and we'll rejoin after 10 minutes with your questions. I hope you have questions today and don't run away.
Sir?
Yeah?
Can I quickly make an announcement regarding a WhatsApp group?
Yes, you are free to do so.
Guys,
so I don't need to listen.
No, not really. Guys, I'd just like to ask, do we have a WhatsApp group for like all of us? Is that a no?
Seems like we don't have.
You don't have it. I'd like to create a WhatsApp group. Excuse me?
No, we don't.
Oh, okay. I'd like to create a WhatsApp group. Could you guys please just take down my number? My number is 060.
Now just 060.
387.
87.
4246. And just like send me a WhatsApp and I'll just create a WhatsApp group for everyone.
So what is your name? What is your name?
Oh, Lupe.
You said from?
Can you call the number again, please? Can you call the number again?
060.
Okay.
387.
Okay.
4246. 46.
Get married. Okay. Not job is kidding us.
Just 060, guys. 387 4246.
Is that 060387?
Yeah.
4246?
Yes.
Okay.
Okay.
Okay,
Thank you.
Thank you very much.
It's my pleasure.
Sure. It was no credit group. So maybe.
Let us resume then. Your questions.
We're started there on these vector spaces. So
our coordinator did not have the number, so we're just off. We're watching it.
Which one?
That first page.
Yes.
The vector space.
Yes.
It starts with V is a vector space, S is an element of V, which is
a subset of V.
Yes. We're not there. We couldn't see anything. Couldn't hear you. Couldn't see anything by then.
Well, this is what we did last time. Last time we discussed what is the span of a subset, and that's this set which I have written down. It is the collection of all the vectors in V which are either 0 or a linear combination of members of S. Okay? We proved that it is a subspace. Span of S is a subspace of S, a subspace of V, and it contains S. So it's bigger than S. And it is the smallest subspace of V which contains S. That's the second line. If S is a subset of P and P is a subspace of V, then span of S is already a subspace of P. Okay? And then the third line says that, well, if you take bigger and bigger sets, the spans increase. Okay? And the span of the empty set, okay? This one follows from 1 and 2. Why is it? Span of the empty set should be a subspace, and it should be the smallest subspace containing the empty set. But we know any subset, any set contains the empty set. So it is going to be the smallest subspace, and that is the zero subspace. Zero subspace means, remember, this was the symbol that we used for this linear subspace, the singleton zero. Okay? So that's the subspace, and so that is span of empty. This one is saying that this line is saying that span of S is equal to S if and only if S is a subspace. So you don't increase anything by taking linear combinations if you are already in a subspace. And if you take span twice, therefore, you don't get back anything bigger. So span of span is same thing as span. Yeah? So these are the properties that we discussed last time, and these are very, very crucial in understanding what span is. That's what we did last time. Okay?
Yes, sir.
Next question.
Prof,
Yes.
Can you repeat that flow chart of the yes and no's? On linear dependence and linear independence.
This one.
Yes, sir.
Yes. So, suppose you are given a list. What do you do? To check whether it is linearly dependent list or linearly independent list. So, you start on with the first element. You ask whether it is 0 or not. If it is, well, it's linearly dependent. You don't have to proceed any further. If not, then you proceed to 2, the second one. And you ask whether the second one is in the linear span of V1, that means it's a multiple of V1. If the answer to that is yes, right? Then you know it's linearly dependent. If not, then whether you are at the end of the list or not. If you are at the end of the list, then obviously this is a linearly independent list. If not, you go back again. So that means you again now from 2 you go to 3. Okay? And there is a little bit of a crisis here. One moment. There is a little bit of a crisis here. There's a little bit of a problem. So let me redraw this. There's a little bit of a problem in this. Yes. What happened? 1 minute. Let me redraw this. So, good that you asked. So, you start off and you ask this question. So, K is 1. Okay? If the answer is yes, it's linearly independent. Sorry, linearly dependent. If the answer is not, then you increase your K. I should write this in the usual computer science way as reassigning. So you reassign K. Should you reassign? No, you should reassign here. So you should ask here this question, whether you are at the end of the list or not. If the answer is yes, then you land up with linear independent. If the answer is no, you reassign your K. Okay? And then you ask the question that, so now your question is first Vk is 0. If your answer is yes, you you come here. If the answer is no, then you ask this question. And what's this question? This question is Vk belongs to span of V1 to Vk minus 1. Okay? If your answer is yes, you come back here. If your answer is no, you will increase, but here. So if your answer is no, you increase. If it is less than n, else you cancel. Okay? So that's your final thing. So after this you stop. Okay? So that's the way. Is V1 0? Yes. Linearly dependent. No. So then the next question, is this all? No, I have another vector, V2. So if you have a vector V2, then you ask your question, is V2 0? The answer is yes, linearly dependent. If the answer is no, the question is V2 a multiple of V1? Answer yes, linearly dependent. No, then again, is this the end? No, I have another one, V3. So again, is V3 0? Yes, dependent. No. Is V3 a linear combination of V1 and V2? Yes, dependent. No, you go back again. So this is the algorithm. It runs through this algorithm, and after n stages, so at most it might require n stages to decide whether this list is linearly dependent or linearly independent. Okay?
So it also says linear dependent, and the second one says linear independent.
Independent.
Dependent and independent.
Independent, yes. So negations at each stage, therefore comes to the conclusion that it's independent. Right? So independent is a kind of, you see, it's a difficult thing to ascertain. Yeah? Thank you, sir. See, in most cases, now that we know that everything is actually, if it is dimension n, it is in Rn, this stage, how do you look into this stage? So, how do you decide on whether Vk is in the span of how do you decide this? That means you have to find such that Vk right? Now, in case when we are sitting inside Rn, say, or say Rn, V1 is an M vector, V2 is an M vector, Vkm is an M vector. So you make this matrix whose first column is V1, second column is V2, the k minus 1th column is Vk minus 1, and so we are going to see how do you do this. So you finally make this matrix apply Gauss-Jordan, as we shall see very soon. Apply Gauss-Jordan and see whether there is a non-trivial solution of this. So we are actually finding spans is nothing else but Gauss-Jordan. Okay? So that's the whole story. Finding spans is Gauss-Jordan. So this will boil down. I have not come to that point till yet. Today was just the starting point in saying that everything now can be boiled down to Rn and matrices. Okay? So ultimately the computational root will be this. So we'll come to it. We'll show that this is the only route out. Okay? So each stage, when you are hitting this block, you are using some kind of Gauss-Jordan algorithm. Okay? So you can say this is actually the Gauss-Jordan part here. We will see that this part, this decision procedure itself is another big flowchart. Okay? So you add these bits and pieces of flowcharts to get your final flowchart. Okay? But you see, it's very, very algorithmic. But to arrive at this algorithm, we have to clean out the basis, the foundations, right? Otherwise, it will be a messy stuff. We will see this. We will see. We will come to this. This we have not come till yet. Okay? So this decision procedure here, either this route or this route, will take us through Gauss-Jordan. Clear? Next step. Next.
Sir?
Yes.
Will it be possible for us to get solution for that bonus questions, last year's bonus questions, so that we can relate with how you ask question and answer them? Because myself...
This year's self-assessments are more or less based on them, but developed further on that. And these lectures are more or less development along the lines of the self-assessment questions. This is number 2. Number 3, you are having this chance of interaction where you can ask questions. So, I don't like giving solutions. I give hints. So either you ask me here, and I give you hints here, or you send me a message, email or whatever, and I write back to you. But solutions, no.
Thank you, sir.
In fact, I think I wrote it clearly in the self-assessments first or second page possibly, that there shall be no solutions. And the reason is nothing else, that you only learn to swim by swimming. Yeah. Next question.
Okay, but what about the main assignments? Are we going to get feedback on the assignments? The main assignments?
Well, in the assignments also, because I think I have told my marker, here he will mark, and he will give as much feedback as possible. You can again come back to me again in the same way. Yeah? So, the same thing works there. Solutions? No.
Sir?
Yep.
Is there going to be a discussion for the assignment?
Yes, if you ask questions, you can do it here. We will discuss.
Okay, sir.
I am here to give you support, but you have to ask the question. I have asked all my questions in the self-assessment, and obviously in the question paper. But you'll have to answer them.
So I have a question about the assignment.
Yes.
In problem 1, right? Problem 1C.
Good.
2 says that, okay, we're supposed to prove equivalence of the 3 things. It says that there exists a function h that with the domain y and codomain x such that h of f equals x.
What are the 3 things?
We need to prove that f is injective.
F from x to y.
Yes, f from x to y.
Okay.
And number 2 is that there exists a function h with domain y and codomain x.
Yes.
Such that h of f equals that capital 1, identity 1, x.
H of f of x. H
No,
composed
h of f. H small circle f.
Yes.
H composed f.
Yes. H composed f is
identity x.
yes.
And number 3 says that for every pair of functions,
Yes.
for every pair of functions, P and Q with domain U and codomain X.
Yes.
If F composed P equals F composed Q,
Yes.
then P equals Q.
Good.
So my question is, with number 2, it says that there exists a function, right? Are we supposed to prove that the function exists, or the thing that exists is a function?
Both.
Both of them.
Yes.
Okay.
Yes.
Okay.
So, could you see that? I'm asking everyone. Can you see that B implies C is immediate? That is immediate. Why? What is B giving you? Suppose if you assume B, then you assume B. So then you know that apart from this F, you have a function H. I drew it in black. So these things are given. So H composed F is the identity of X, right? Okay? Now you are starting with C. You are saying that whenever you have two things coming into X, and you assume that F composed P is equal to F composed Q. Well, if this happens, then obviously H composed F composed P is H composed F composed Q, right? Clear? Now, the composition is associative. So this means but you have told me H composed F is identity. But P composed the identity of X. Remember, identity of X is something here. From X to X. So P composed identity of X is actually P, and this is actually Q. So you see, P implies P is trivial. Yeah?
Sir, can I please ask, is that also how we prove, does that also show that number 3 implies number 1?
Correct.
Are we going to use the same thought? Okay.
Correct. Yes. Exactly so. You have to just choose suitable functions P and Q. Correct. It said whenever you have two functions coming into X with the condition F composed P is equal to F composed Q, then P is equal to Q. So as if it is saying F is less cancelable. You can cancel it off from the left. Right?
Excuse me, sir?
Yeah.
What does left cancelable mean?
Oh, I just made it up. As if you see, if you have this equation, F composed P is equal to F composed Q, so you're as if cancelling off F from the left hand side. You have just erased it, and you came to the conclusion P is equal to Q.
Oh, okay.
Okay. I just made it up. So therefore it is something like saying something like that. As if it is left, you can cancel it from the left.
Okay. And then, sir, my last question is, so do you perhaps have like the actual task next to you, the assignment?
What is it?
Do you have the assignments nearby?
I don't have them, but you can tell me.
Oh, okay. I'm struggling with understanding, like, you know, we have like a little explanation after problem 1. I'm struggling to understand like half of what point 2 means.
What is it? What is point 2?
It says that the function f has an inverse from the left, or is left invertible. Okay, I understand that part now. Recall that x line identity x is a function defined by...
Yes.
I don't know how to say these things, sir. Is the function defined by identity x equals x? And hence...
Wait. Remember, whenever in my definitions or in my symbols, when I write something like this, I mean actually that f is a subset of x cross y, and which subset? It's a certain subset of x cross y, right? And it has several properties. First property is, for each x in x, there is a y, and so on. And the second one is, if x and y and xy prime are both in F, it means that y is equal to y prime. Okay? So, this set F looks like this. It's a pair x and y, but for a fixed x, this y is unique. Alright? And this unique y, we will usually write it as y equals fx. Okay? So, another way to write this function is like this. Okay?
Yes, sir.
So what is f bracket x? It is that unique y such that the pair xy is a member of f. That's the whole meaning. Now, coming to your question. So what is identity x? Well, identity x is going to be a subset of x cross x. And what is that subset? That subset is nothing else but xx. And that's why, as we said, identity x, this function, bracket x should be x. Okay? That's one way of writing it, or another way of writing it is this. Okay? So do you understand the notation now?
Yes, sir, I do understand the notation, but my problem is with I understand everything you say. I'm struggling to understand how it links up to everything, like question. Am I making sense?
No, I need to be guided a little more. Because I said that when I wrote this line, remember there is another thing over here. When you have two such things, remember F is a certain collection of x cross y. So is G. Now, this composite function, which I am writing as G circle F, this is also a subset, but now of x cross y. And what is this subset? This subset looks like x G of f of x. Remember your f was your G was so this is your G composed. So we write therefore G composed F evaluated as x is G f of x. Yeah? So now I have something to say about this composite and this. So I am saying this whole thing therefore means that H of f of x, that's H composed f at x, and 1x of x is x already. So this statement B is saying that there is a function h from y to x such that h of f of x is x. So as if it is, in fact I am drawing it for you. Here is my x, here is my y. Remember, the best way to represent a function is by this stock diagram. Right? This is a general function, how it looks like. Now I want a function from this to this side, such that if I start with any point, this is my h. So I want something. So I start here, I come back here, and when I go back, this equation tells me I have to go back here. Right? So now think, how does injectivity add to this? For instance, this I don't know where to take, because, but for instance, if I started off here, I go here, and I know how to go back. I know how to go back here. That's immediate. But this point, these points, the several points over here are all mapped here. So where do I go back? That's my real issue. Okay? And now think, how does this connect with injectivity and so on? And then you will get hold of the answer.
Okay, sir.
You just draw this, and then you will see.
Oh, sir, I have another question. You know, with the assignment, right? I'm struggling on how am I supposed to, can I use my logic to, can I just write down what I'm thinking? I don't know if that makes sense. I just write down what I'm thinking in words instead of mathematical notation.
Okay, you first do it, but slowly down the course, you will have to slowly change your writing by putting in these symbols. Now, the only reason why I stress so much and I'm so pedantic about symbols is that words often make dual meaning, but this strict use of symbols make it very simple. So, you'll have to make this translation slowly. It's a difficult process, I understand, but you have to go through this exercise of translating what you're thinking into this symbolic language, and then very soon, once you have done it, you will see that symbolic language is the easiest to think.
Okay, sir. Thank you, sir.
Yeah. Next. Next question. Okay. If not, if there are no other questions, then we can disperse.